This is Mrs. Damavandy. We're going to go over section 3.2 on linear functions. First, these three vocabulary words you need to understand, and the idea of linear versus nonlinear. So a linear function is a function whose graph is a non-vertical line which has a constant rate of change and can be represented by a linear equation in two variables. So it can't be a vertical line. Constant rate of change from last year, hopefully you remember that means slope. So it's a line that's not a vertical line that has slope and can be written in an equation with x and y. Those are our two variables. A nonlinear function does not have a constant rate of change, so its graph is not a line, not a straight line. Okay, so linear, graph is a straight line, nonlinear, not a line. Constant rate of change, which is how we get slope. But slope is derived from the idea that as the x changes by a constant amount, the y also changes by some constant amount. So x and y both increase constantly, and we get this constant rate of change, which is the slope of the line. If the table has a constant rate of change, then it is a linear function. So to check if a relationship between x and y, like on a table like these, are linear or not, you could plot them, or you can just figure out constant rate of change, if it has one or not. If we look at the first table on the left, we're going from 3 to 6, which is increasing by 3, then 6 to 9, also increasing by 3, 9 to 12, increasing by 3. So the x values are changing constantly. We just need to check if the y values are also changing by some constant amount. So from 36 to 30 is decreasing 6. From 30 to 24 is also decreasing 6. 24 to 18 is also decreasing 6. So we can see this relationship on the table. The x changes by a constant amount every time. The y also changes by a constant amount every time. This is going to be a linear function. We can even use this change to calculate what the slope will be. The slope is going to be the change amount in the y variables divided by the change amount for the x variables. So it will be the change in y is -6, the change in x is +3. When you divide that, we would get -2 would be the slope of this function. If we look at the table on the right-hand side, if we check the x values, 1 to 3 to 5 to 7, that's all increasing by 2 every time. But as x increases by 2, we have the y values. This first jump is an increase of 7 from 2 to 9. But then when we go from 9 to 20, that's an increase of 11. And then 20 to 35 is an increase of 15. So this is not changing constantly. The change in the y values is growing. So this will not be a linear function. It'll be curved somehow. You can plot it out and see if you want, but the point is just figuring out which one's linear, which one's not. All right, which can be written in the form of y equals mx plus b. All linear functions can be written in an equation of two variables, y and x. And if you can write it in this form, y equals mx plus b, this is called slope-intercept form. It's possible to write all linear functions in slope-intercept form. Okay, so right here, this is slope-intercept form. So we're seeing 4 variables instead of just the 2 that I'm talking about, x and y. That's because this is a general form equation for all linear functions where we're saying m is really going to be some sort of slope value and b is a y-intercept value. So you graphed a lot of equations like this last year, and we're still going to be working with graphing equations in slope-intercept form. If we look at this first equation right here, y equals 3.8. Okay, this can be written in y equals mx plus b if we do a little work and rewrite it as y equals 0x plus 3.8. It's just that the slope of this line is 0, which means it's a flat horizontal line that goes through the y-intercept 3.8. So this one is linear, and yes, it can be written in slope-intercept form. The second one right here, y equals the square root of x. This is not a linear function because this square root is actually a 1/2 power on the x. If x has any power other than a power of 1, then it is non-linear. So this was number 1 was a yes, it can be written in slope-intercept form. This number 2 is a no. If we look at number 3, so the x is in the denominator. It is dividing the 2. This is also the same as y equals 2 times x to a negative first. If you can remember exponent properties from last year, you learned that when you have negative powers on the x, it means that you reciprocate it or put it in the bottom of the fraction or flip it. And again, what I was saying earlier, if x has a power other than a 1, other than a positive 1, it's not going to be linear. So this is a no as well. So with this fourth equation up here, the x is the exponent of the 3. So this is y equals 3 to the power of x. This is not linear because x is in the exponent. This is actually an exponential equation. We'll learn how to graph those later in this year. So this is also a no. This cannot be written in slope-intercept form, and it's not going to be linear. This fifth equation right here, if we distribute the x, we see that this not the x, the 6 in front of the x minus 1, we see that this equation is y equals 6x minus 6. This is exactly slope-intercept form. We can see that the slope is the 6 right here, and the y-intercept is this negative 6 right here. So this is a yes. All right. This sixth equation, x and y are on the same side of the equal sign, but you also see that x has a power. And earlier I've said if x has a power other than just a 1, so that it just looks like a regular normal x, it's not going to be linear. But this also doesn't have x and y being on separate sides of the equation. This is what's called more of a standard form equation because of that reason. But still, it's a no. And we'll look more at standard form equations where x and y are on the same side in the next section, chapter 3. All right. There's 2 different types of domain. There's the idea of a discrete domain and the idea of a continuous domain. A discrete domain is a set of input values that consists of only certain numbers in an interval. What that means, if we think of decoding this, I guess, input values are talking about x values. So is domain, okay? When you hear domain, when you hear input, when you hear x, those are all connected. So we're talking about our x's. Set means like a group of numbers for our x. So we're looking at a group of numbers that are our x values, and then there's only going to be certain numbers in an interval. An interval is when we're looking at like starting at this value, ending at a different value. If you take a second to look at the 2 graphs at the bottom, see how the first dot is at 1 and the last dot is at 5 on both of them? So these number line graphs, we're looking at the interval of the values from 1 until 5. But on the discrete domain graph, we don't have all of the values 1 through 5. We only specifically have 1, 2, 3, 4, and 5 that have been graphed on this number line. The difference in this continuous domain on the right is that you have all of the numbers in an interval. So this interval from starting at 1 up until 5, every single number is plotted on this number line because we have a solid line from one end to the other. So I mean any number. So like 3.457, any number, any um, real number between 1 to 5 is in this interval. So since we continuously start at 1 and end at 5, this is a continuous domain. Versus the idea of discrete, which is just um, some points, some numbers within the interval. All right, let's look at this story problem. The linear function y equals 15.95x represents the cost y in dollars of x tickets for a museum. Each customer can buy, wrong buy, should be buy. Each customer can buy a maximum of 4 tickets. So in part A, we're supposed to find the domain of the function and tell whether it's a discrete domain or a continuous domain. So the domain of a function really depends on the real life context of the problem, not just the equation that we're using to represent the function. Because we have this equation, y equals 15.95x, and if you graph that, you would just get a straight line that continues all the way to the left, all the way to the right, because lines continue in both directions forever. And if the line continues, that's the idea of a continuous domain, because you can have any x value in like anywhere, because you don't have just points here and there. It's every single point connecting up to make the whole solid line. But the context of this problem says that we can only buy a maximum of 4 tickets. And tickets is our domain values of x, the number of tickets we can buy. So if we actually think about how many tickets can we buy, a customer could purchase 0, they could purchase 1, 2, 3, or 4. 4 tickets maximum. So these are our domain values, because we can't purchase 1.5 tickets or 2.75 tickets. So we're stuck with a discrete domain on here. The domain is discrete. And then part B, we're going to graph the function using its domain. So instead of graphing this entire line by using slope and y-intercept, we just really need to figure out 1, 2, 3, 4, 5 points. We need to figure out 5 points, where x is 0, what's the y value? Where x is 1, what's the y value? 2, 3, and then 4. And then if we plot these 4 points, we've graphed the function over this specific domain. So buying 0 tickets is going to be $0 in cost. Buying 1 ticket is $15.95. And then if we double that, the cost for 2 tickets is $31.90. The cost for 3 tickets is $47.85. And then the cost for 4 tickets is $63.80. So 0 is going to be down in the corner over here. 1 ticket and $15.95. So here's 10. Here's 15, halfway between. So I'm just going to go a little over where 15 would be. 2 tickets is $31.90. So I'm going to go a little over 30. 3 tickets was our $47.85. So here's 40. Here's 45. $47.85 is somewhere over here. And then for 4 tickets, the cost is $63.80. So 60, that's 65, let's say 63.80 is right there. So you can see these dots form a straight line, and they should, because this is a linear function. It's just that we're not connecting them to draw a solid line. If we did, we would be saying, so let me get a different color. If we did draw a solid line, we would be saying that every single point I'm going through is a part of this function. So like this point right here, for 1.5 tickets, I could purchase 1.5 tickets and it's almost $25, but I can't in real life. So that's why It's just these 5 points. Okay? Let's do another story problem. A cereal bar contains 130 calories. The number of C calories consumed is a function of the number of B bars eaten from a box with a total of 6 cereal bars. So does this situation represent a linear function? Explain. So to be a linear function, you have to have a constant rate of change. Okay, and it's a non-vertical line with a constant rate of change. So you have to think about, are the number of bars that we're going to eat, can it change constantly? And is the number of calories consumed by eating those going to change constantly? So like if you look on a package of like granola bars, you have all of the information for how many calories per bar. The number of calories should be the same for each bar. So if we eat one bar, we get this many calories, 130. Eat another bar, that's another 130 calories. So it is constant. So yes, it is going to be a linear function. So if we move on to part B, find the domain of the function. Is the domain discrete or continuous? All right. So we got to think of what's realistic for the number of bars we're going to eat. It's really easy to say we could eat 1, 2, 3, 4, 5 bars, 6 bars total to eat the whole box. And yeah, you could make the argument that you could eat 1.5 bars. But we'd have to like cut them up. And who's going to eat a part of a granola bar? If you get one, you're probably going to eat the whole thing. So the most realistic domain is going to be if you eat 0 bars, or 1, or 2, or 3 total, or 4, or 5, or all 6 from the box. Can't go to 7 because you're just going to say here's our one box of 6 cereal bars, okay? So this would be a discrete domain. And then plus, it'd be really hard if you're like trying to get 1.8675 of a bar. So it's best to just work with a discrete domain. So over this domain, we're going to graph the function. So we just need to figure out how many calories for each number of bars. So if we have 0 bars, it's going to be 0 calories that we've consumed. If we have 1 bar, it's going to be 130. So this is about 150. So 130 is going to be about right here. Okay. And then if we eat 2 bars, add on another 130, that's going to be 260. So that's going to be about right here. If we eat 3 bars, so 3 bars at 130 calories each is 390. So that's 350, that's 375, 390 is really close to 400, so I'm going to put it about right there. And then 4 bars. 4 bars, 130 calories each is 520. So it's a little under 525, which is about right there. 5 bars, 130 calories each is 650. So that'll be dead on right there. And then if we eat all 6 bars in the box at 130 calories each, that is 780. So that's 775. Go a little above it. Say that's 780. So again, we can see that this forms a straight line, which makes sense because we said it would be a linear function. We just don't have all of the points in between these ones as being part of our domain and range because it doesn't fit the context. Awesome. That's our last example. If you need to watch this again, you can find it on Google Classroom and any of the other previous videos. Hopefully now you guys can get started on some of the worksheets. Okay, bye.